Hello, welcome to Engineer's Edge GD&T applications. So what we have here is a shaft feature, and this shaft feature will rotate about a couple of bearing features in the mating part, and those diameters are defined as our 24.5 to 23.4. We also have a secondary bearing feature, size 24 to 23.9. And what we want to do is to relate another diameter at this 19 to 18.9 back to those two bearing contact features. So this shaft feature is driven by a spline on the left side, and these are relatively close tolerance features. Now we are working in millimeters, and what we need to do from an application point of view is to define the datum features based on the functional requirements of this component. So since we know that these two diameters are those datum features which we mate to, then those are going to become our datums. So let's go ahead and identify those, and the way that I'm going to do this is simply attach my datum symbology to my size dimension, and I'm going to call this feature on the right side of the part datum B. And then I need to relate my datum features to each other. Now, since this is a simultaneous requirement in terms of the assembly and the functionality, I'm going to relate these two datums to each other. I want to control the form as well. So what I'm going to define is a total run out, and in this case a relatively tight tolerance, and follow my datum structure, if you will. Let me finish identifying what these are. So I've got a total run out of 0.02 relative to a datum element A-B, and then my datum A is going to be defined the same with a total run out of 0.02 regardless of feature size relative to a datum element established from datum A-B. And the diameter, which should be related back to these datum features, I'm going to control that as well with a datum single axes. And let's take a look. In this case, our application is not as critical since this is going to be relatively a press fit, but I'm going to say a circular run out of 0.2 in regards to feature size relative to datum established from A-B. This controls the form of each circular element as well as ultimately the size, if you will, from 19 to 18.9. So what is this saying? It may seem circular logic to you, and that this datum A-B in terms of B relates to A and A relates to B. What you need to be aware of is that when a regardless material boundary is applied to a geometric tolerance, and in this case we have multiple datum features of size, so that would be the 24.5 to 23.4, the 24.0 to 23.9, that the datum feature simulators for each of these features is located and oriented at a fixed distance relative to each other. And what happens is that these datum feature simulators will In this case, they'll contract, but if we had an internal feature of size, they would expand simultaneously from their maximum material boundary size to their least material boundary size until the datum simulators will make maximum amount of contact with the extremities of these two as-built datum features. So what I want to do is illustrate what those datum simulators might look like two-dimensionally. So we would have a cylinder of some flavor that collapses onto datum A until we get maximum number of points of contact, while simultaneously our datum B simulator is a cylinder that collapses as well until the maximum number of contact elements with the extremities of that as-built feature is established. So what we're effectively doing is we're creating a single datum axes or element from both datum B and A simultaneously, to which we're going to measure all the surface elements of a total runout on our datum B feature as well as our datum A feature, and then ultimately relate back our diameter of 19.0 to 18.9 back to those two datums being treated as though there's a single datum feature. Thank you for watching Engineer's Edge, GD&T.